Hey, what's up, guys? All right. So, tonight we are going to keep on. Tonight we are going to keep on. Oops. There we go. Okay. So, tonight we're going to keep on with our discussion of section. Chapter 4.1, and we're going to talk about residues a little bit more, how to calculate them. Last time we got a few different methods, mainly to do in the case of simple poles. Now, double poles, poles of order 2, things, we had removable singularities, we had simple poles. Now we're going to get on to poles of order 2, 3, 4, all the way on up, and then we'll briefly discuss the difficulties inherent to dealing with essential singularities. So, before we do that though, the homework that was due on Monday, if you recall, I moved back till tonight because I got a number of questions about it, and by far, problem 3 and problem 6 were the two problems I got the most questions on, so it seems reasonable to really quickly, since people probably had questions who didn't ask, it seems reasonable to at least kind of address these guys really quick. So I figured it might be useful just to kind of go through it. Let's do 3 first, where we were talking about a function f of z, which is written in terms of a power series centered at 0. And we're assuming that it converges for modulus of z less than big R. So for a little r between 0 and big R, so something inside the disk of radius big R centered at 0, we want to show that f of z is equal to this, where z is equal to r e to the I theta. I think nobody had any problems with that. You just plug r e to the I theta into f of z and you get out, well, just, r to the n e to the I and theta, right, for that piece. And that's exactly what's right there. So I don't think anyone had any problems with that, but we wanted to show that the formula for the terms here is given by this, and then we wanted to show this nice equality holds. So this is Parseval's theorem, this top part. And the bottom part is known as the energy form of Parseval's theorem. So to do the first part, the trick is not that bad. Basically what we're going to notice is, so to start with, we'll take 1 over 2 pi r to the n integral from 0 to 2 pi f r e to the I theta times e to the minus I n theta d theta. So start with this piece, and we'll just do some basic manipulations. What I'll do first is I'm just going to bring this r to the n on inside, and I'm going to write this on the bottom of fraction to get rid of that negative from the exponent. So this will turn into the integral from 0 to 2 pi, and I still have that 1 over 2 pi out front. And then I have f r e to the I theta. There is a little dot right there that shouldn't be there. R e to the I theta over r to the n e to the I n theta d theta. Okay, now what I'll do is I will rewrite this really quick as 1 over 2 pi integral from 0 to 2 pi f r e to the I theta over r e to the I theta to the n d theta. Okay, now what I'm going to do is I am going to try to get rid of this d theta so I can write this as some kind of a contour integral, right? So the trick here is that since I see r e to the I theta, I'm going to assume that I'm going about a path gamma of t, where gamma of theta, where gamma of theta is given by r e to the I theta. That is, I'm going around a circle of radius r centered at 0 counterclockwise. So what I'll do here, since I have to obviously convert my d theta into a dz, is I'll notice that the derivative of r e to the I theta is I r e to the I theta, right? So I need to get an extra one of those. Fair enough. What I'll do for that is I'll just multiply the numerator and denominator by that. So integral from 0 to 2 pi f r e to the I theta over r e to the I theta, all of that to the n. And then I'm going to multiply this whole business right here by a clever form of 1, which will be I r e to the I theta over I r e to the I theta d theta. Okay. Now this is just going to, I'll leave this 1 over 2 pi right here. Notice that I can bring this r e to the I theta here into this one, right? So that'll just be, I'll rewrite this really quick. I'll even bring this I outside if you don't mind. I'll bring that out here because it's just a constant I won't need. I'll have r e to the I theta to the n plus 1 on the top. I'll have f r e to the I theta, of course. This is still from 0 to 2 pi. And then I will have at the end of it I r e to the I theta d theta. This is just going to be our dz. All right, so I get 1 over 2 pi I integral about gamma of f of z over z to the n plus 1 dz. Everyone follow that step? Yeah, probably. Good. Okay, and notice by Cauchy's integral formula, this is just the nth derivative of f at 0 all over n factorial. But hey, if f has a representation as a power series, it's analytic. So if it's got a representation as a power series in this region, it's analytic. All good. All right. So there we go. And now by analyticity, it's got a Taylor series. And by the uniqueness of the power series, we know that the ANs are given by these terms, right? Okay, so we've got what we want. Bada boom. So the uniqueness of the power series part I'm referencing is just the whole business where you've got like an z minus z naught to the n equals, terrible sum right there. Bn z minus z naught to the n, then this tells you that an is equal to bn, and vice versa, obviously. So that's just a little aside right there. But that would give us this first part right here, where we get the formula, right? Having a Taylor series and doing this calculation, these are the coefficients in the Taylor series, and so the coefficients in the Taylor series have to be the same as the coefficients right here. We're all good to go. The second part is the part that I think people might have found a little bit more tricky, and I saw a lot of incorrect answers in submitted things, so it seems reasonable to bring it up really quick. What we're going to do here, we have 1 over 2 pi integral from 0 to 2 pi modulus f of r e to the I theta squared d theta, and we want to show that it's equal to the sum of n equals 0 to infinity of the modulus of the coefficients squared times r to the 2n. Okay, so let's start out with 1 over 2 pi integral from 0 to 2 pi modulus f r e to the I theta. Let me make sure I get this right. I theta, yep. Squared d theta. Let's start out right here. Okay, now here's where I think a lot of people maybe didn't know what to do. What we're going to do is I'm going to rewrite this as f r e to the I theta times f r e to the I theta, or f bar r e to the I theta, right? Since modulus z squared is equal to z bar, modulus f r e to the I theta squared is equal to is equal to f r e to the I theta f bar r e to the I theta, right? Where f bar is just if f is written as like, u plus iv, it would be u minus iv, right? So let's do that. Okay. Integral from 0 to 2 pi, and we'll do that. But just to save ourselves a step and a little bit of time writing, let me write out f r e to the I theta as sum from n equals 0 to infinity a n r to the n e to the I theta n. Okay, and I'm going to write out f bar r e to the I theta as, well, just the conjugate of this, right? So n equals 0 to infinity. This will be a n bar r n, since r is just real, and e to the minus I theta n d theta. Okay, now notice I'm multiplying these two big products together right here, right? Each of these is defined in terms of limits, yeah? So we've got basically, you know, some situation, like imagine you have like the limit of like, you know, as, we'll say like, you know, write it as like k goes to infinity of like gk. Let's say that this is equal to like g, and the limit as, I don't know, let's pick another variable, t goes to infinity. You say like ht is equal to h, right? So just generally, if you have something like this, notice that gh is equal to, well, limit of these gk's times the limit of these, that's a t, sorry, that's a terrible t, as t goes to infinity, of these ht's, right? So notice I could, of course, replace one of these, say like with like, oh, let's replace this h, this limit right here with an h, right? Well, I could bring that on in here since it doesn't depend on k, right? And I have limit as k goes to infinity of like gkh. Okay, that's fine. And now, hey, I could, you know, bring back in the limit, right? As t goes to infinity of gkht, right? Something like that. So you can see that, you know, and I'm skipping a step here where the gk would be out front and then I bring it inside the limit. But basically what I'm trying to say is that, look, you can put it all together, right? And since these guys, these series, are defined in terms of limits, I'm going to do exactly that. An easier way to think of this is that I'm multiplying this entire series right here by each term of this and summing it up, right? So naturally I could just sum up those multiplications, right? So integral from 0 to 2 pi of the sum from n equals 0 to infinity a n r to the n e to the I theta n oops, I messed up right there. I'm rewriting too fast. And then I'm going to use something instead of n. I'm going to use like k. How about that? So I don't get anything confused. I'll do now a n r to the n e to the I theta n a n bar r to the n e to the I minus I theta. Oh, sorry, these should be k's, not n's, since I'm using a different index. I theta k d theta. So now I've just got this kind of double sum. Now, before I continue, let's notice something. So I've got this chunk right here, right? Okay, now, here, I'll write this down here. A n r to the n e to the I theta n, a k bar r to the k e to the minus I theta k. Okay, now when n equals k, this is just, well, an bar, that's an modulus squared, r to the 2n, and hey, those guys will cancel each other out, right? But when n is not equal to k, notice what you get is you get, you know, like an, a k bar, r to the n plus k, e to the I theta n minus k, yeah? Okay, now if I integrate this guy, what do I get? Say if I integrate it from 0 to 2 pi, a n a k bar r to the n plus k, e to the I theta n minus k d theta. Well, let me just pull out all of this business right here. I'll just get an ak bar r to the n plus k, integral from 0 to 2 pi, right? And then this is just e to the I theta, notice, to the n minus k, d theta, right? What is going on? Well, what do I get out of this? Notice I've got when n is not equal to k, this is not equal to 0. So obviously I could pull out, these guys are equal. I'm trying to be clear here. I'm writing my equals vertically. an a k bar r to the n plus k. And now here's what I'm going to do. 0 to 2 pi. Now this will be e to the I theta. And I'll write it as n minus k minus 1, right? How about that? Something like that. And then I'll have, now this will be, I'll pull out an extra e to the I theta. And in fact, maybe I'll put these guys over like I, so I can put an I right here, d theta. And then, hey, would you notice that this is like an ak bar r to the n plus k over I, integral 0 to 2 pi, or I'll even get rid of the 0 to 2 pi. So it's about a curve gamma, is e to the I theta, z to the n minus k minus 1, dz, about the unit circle. What is that? It's 0 by Cauchy's theorem. In the other case, though, this, we might not get 0, right? In fact, we know what we'll get. So this piece right here turns into 1 over 2 pi, and I'm going to bring these integrals on in through the sum, and it will just turn into the sum for when n equals k, right? So I'll just get those terms where it's the same, and I'll have the integral of an bar squared r to the 2n is from 0 to 2 pi d theta. I can obviously pull these constants out, and then I'm just integrating 1 from 0 to 2 pi. What do I get out? 2 pi, the length of it, right? 2 pi. Oh, wait a second. So I have 1 over 2 pi times the sum from n equals 0 to infinity of 2 pi times an in modulus squared r to the 2n. But hey, cancel, cancel. I've just got the sum from n equals 0 to infinity of modulus an squared r to the 2n. And wouldn't you know it, that's what we want, right? So I saw a lot of those that were, people were having a lot of trouble with that one. And so it seemed like a good thing to bring up. It's kind of a long diversion right there, but it's worthwhile since we don't have too much left to cover in the section today. The other one that I saw people having a lot of trouble with was 6. I won't go into nearly as exhaustive of detail here, but I will kind of outline how to do things. These are both great ones. They really show a lot of what's going on, and if you feel like you're struggling with some more of these power series things, please take extra time to get used to it, because you will have to use these techniques to a modest extent throughout at least the rest of the class. And there's also fantastic things to have in your tool belt. So this Taylor series problem is basically to figure out how to prove L'Hopital's rule in the complex plane using Taylor series. We're assuming that f of z and g of z are analytic and both have zeros of order k at z naught. Then f of z over g of z has a removable singularity. That part's obvious. You can just get that straight up from a proposition in your textbook. And the piece that we need to prove is that the limit as z goes to z naught of f over g is equal to the limit of the kth derivatives. And in case anyone got confused by this, I keep forgetting to fix this, at z naught, not at z. I'd hope everyone at this point would not expect to see a z without the z naught here if we're taking a limit as z goes to z naught. Sorry about that mistake. Anyways, so how do we do this? Well, basically all we do is we use, I think it was like theorem, I don't know, like 3.2.9 or something like that, 3.2.6, I don't remember. And basically by analyticity and having zeros of order k at z naught, then in some disk of non-zero radius centered at z naught, we got that f could be written as z minus z naught to the k times some analytic function phi of z, which is non-zero at z naught, right? Similarly, same exact thing with g, potentially on a different disk, but since they're both centered at z naught and have non-zero radius, their intersection is, non-trivial, and different function psi here. But similarly, phi and psi are both analytic and non-zero at z naught. Okay, so in this case, all we have to do now is just take the limit as z goes to z naught of f of z over g of z, and it becomes super obvious exactly what's going to happen, right? Well, these guys will cancel out, and we just get phi of z naught over psi of z naught, since neither of those guys are 0. Super simple. Okay, so now what we have to do is we have to show that these guys are equal to, what have I done? Equal to the kth derivatives of each respective function at z naught. Okay, we'll just do it for f, since we could, do exactly the same process for g, and then it'll generalize. So since f can be written at z naught in the following form by Taylor's theorem. I should use a variable other than k here, sorry. Since we're using k for this order of the 0, let me use, say, n, how about? There we go. So there we go, that's by analyticity, Taylor's theorem. Okay, cool. And then since f has a 0 of order k, has z naught as a 0 of order k, notice what this means is that f of z naught equals 0, and so does, maybe I write it like this. Let me write it as f of z naught equals f prime of z naught equals dot 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 all the way up to f k minus 1, the k minus 1th derivative at z naught. These guys are all 0, right? So k is the first non-zero term in the Taylor series, right? That's the first derivative that's not 0 in this Taylor series. Okay, cool. It's the first term in the term in this sum defining the Taylor series, for which the coefficient is non-zero. Okay, so really I could just take this and start it at k, right? Okay, but wait a second. We know that f is also equal to z minus z naught to the k, phi of z. Oh, wait. I could just divide both of these by z minus z naught to the k. And hey, what have I found when I do that? Well, if I do that, then I get that phi of z is equal to, and now when I do this, I'll write this step out. N equals k, infinity, f of n z naught n factorial, z minus z naught to the n minus k, right? Just dividing everything by z minus z naught to the k in this series here. Okay. Now I could reindex this and just write it as the sum from n equals 0 to infinity of the n plus kth derivative of f at z naught over n plus k factorial z minus z naught to the n. And hey, I've got a power series for phi, right? Oh, wait a second. So this just means that phi of z naught is just the first term of this, which is just the kth derivative of f at z naught over k factorial. We're going to get the exact same business for psi of z naught with g. We'll get the kth derivative of g at z naught over k factorial, and just conduct a simple division here like this. Just basically erase those. Put this right here, and we just get exactly what we want, the kth derivative of f at z naught over the kth derivative of g at z naught. And bada boom, that's how we prove L'Hopital's rule in the complex plane using Taylor series. So those were far and away the two problems that people had the most trouble with. And with that out of the way, let us get back to our regularly scheduled lecture. Hopefully I can kind of make this a little tiny bit smaller. Oh, there we go. I need to, yeah. Boop, there we go. Okay, cool. Now I have more room on the screen. All right. So last time, if you recall, we used this Laurent series kind of form of Cauchy's formula, Cauchy's theorem. This is the residue formula. It tells us that if we have f analytic on a region A, except potentially at an isolated singularity at z naught, with residue b1 at z naught, then for any circle about z naught in A, we have that the contour of an integral of f about that curve is equal to the residue times 2 pi I. All right, kind of exactly like Cauchy's theorem. We got a couple of ways to deal with this for removable singularities and for poles, that is, or for poles of order 1, simple poles. What this turned into was we were looking at the residue of f at z naught was something like, if we had, the best one was this theorem right here, this last one we did. Proposition 4.1.3. So if g had a 0 of order k at z naught and h has a 0 of order k plus 1, then we had a simple pole with residue given by, for g over h, by k plus 1, kth derivative of g at z naught, k plus 1th derivative of h at z naught. So just take one more derivative on the bottom, multiply by k plus 1, and there you go. Notice that this formula up here is just a special form of this one. So this really is the better one. And indeed, if you want to be fancy, you can do the removable singularity piece and see that you kind of get the exact same thing out of here. Now what we'll do is we'll deal with a little bit higher order poles. So double poles is the next one. This will be fun. We'll get a little bit of good stuff in here. All right, let me get a better highlighting color. That's a nicer color. Drop that opacity down. So double poles. All right. Now the formula for residues at double poles is a little bit more complicated. It's not too bad, but it is a little better. It's a little bit harder. So we'll do double poles. We'll give you a formula for it. Then we'll just kind of give you a general way to approach higher order ones. That is, it's all right. So let's start with proposition 4.1.4. Here we have g and h analytic at z naught, and g of z naught is non-zero, h of z naught is 0, as is its derivative, but its second derivative at z naught is non-zero. Then, of course, g over h has a second order pole at z naught. That's kind of what the definition is, right? And the residue is equal to, oh, this is crazy. It's a wild formula. It's not too bad though. 2g prime at z naught over h double prime at z naught minus 2/3 g at z naught h triple prime at z naught divided by h double prime at z naught, that whole quantity squared. Oh God, do I have to memorize this for the test? No, don't memorize this for the test. In fact, probably maybe use it like, I don't know, once or twice ever in your whole life, or maybe never in your whole life. It is, you can get a closed form, right? It's kind of like the way I think of this is kind of like, there's the quadratic formula. There also is a cubic formula and even a quintic or quartic formula, no quintic or higher. But no one knows the cubic or quartic formulas. Though they exist, they are long and they are pretty brutal, so we almost never use them. Maybe you might want to use them in like a computer program or something like that, but we don't have to deal with that here. So you just know they exist. You can use them if you need it. You can go look it up here if you need to. There are slightly more general versions of this. Proposition 4.1.5, if G and H are analytic at Z naught and G of Z naught is equal to 0, G prime of Z naught is non-zero, and H of Z naught is 0, H prime of Z naught is 0, and its second derivative is also 0, but its third derivative is not. Oh, wow. Then G over H has a second order pole at Z naught with residue 3 G prime, double prime of Z naught, over H triple prime of Z naught minus 3 over 2 G prime of Z naught H, the fourth derivative, over at Z naught. They use IV. Don't be confused by that. We might as well write 4, right? Fourth derivative at Z naught divided by the third derivative of H at Z naught squared, that whole quantity. Okay, this is nutso. Notice here we're assuming that G of Z naught is non-zero. Here we're saying it is, but its derivative isn't. And then we're adding one more zero derivative to H, right? Okay, so it's another crazy formula, right? Notice over here, it looks like some kind of formula similar to this. Doesn't have this other term. You might be looking at this and being like, what is going on? Why is this messiness? What's happening? This seems nightmarish. Do I have to memorize all of these things? Is there some good reason I should know all of this? And the answer is no. It's good to know that these things exist. It is good to know that it is possible to find formulas like this, and it is occasionally useful to use them. For example, if we want to do a little bit of working through some problems, we might as well, really quick, take, say, e to the z divided by z minus 1 squared. This is a second order pole at z naught equals 1. I mean, at the top is non-zero, bottom has a 0 of order 2, right? So second order pole, right? Okay, so g of z is obviously the top, h of z is obviously the bottom, and I'm using white to highlight. That's a bad thing to do. There we go. So g of 1 is e, that's non-zero. H of z naught is 0. That is, plug in 1, you get 0. Take a derivative. I'm still going to have a z minus 1 term in there. I'm going to get 2 times z naught minus 1, so 2 times 1 minus 1. I will still get 0. But when I take one more derivative, then I will just get 2, and that's non-zero. So what I'll use is I'll use proposition 4.1.4, and I'll just compute this ugly nightmare. So 2 times the derivative of the top function at z naught, so that's going to be e to the 1, 2 times e to the 1 divided by second derivative of the bottom, that's just 2, so it'll just be 1, right? Or e to the 1, minus 2 over 3 times the top function, which at 1, which would still just be e to the 1. Oops, I'm using the right formula. Third derivative there, and that will just be 0. Then on the bottom, the second derivative at z naught, which is just 2, square that quantity, but we got a 0 on top. What do I get out of it? I just get that e from the first one, bada boom, e. That's the residue. The residue of e to the z over z minus 1, that quantity squared at 1, is equal to e. Kind of cool. Not that cool. This is not necessarily a part that you're supposed to feel like is neat. This is a part that's supposed to feel like maybe computation is occasionally tractable. But these formulas are kind of rough, and we can do some more examples. We could do e to the z minus 1 divided by sine cubed z and apply the next formula, this whole business right here. If you are interested in that, we can go through and confirm that if we take g to be e to the z minus 1 and h of z to be sine cubed z, then notice we have all of the nice conditions for everything to work for proposition 4.1.5, right? And then if we do computation with the fourth derivative of the bottom function and plug everything in, we will just end up getting a residue of 1/2. I'm not going to say the calculations there because they're kind of annoying to go through, right? But you could use it if you needed to. All right. What about higher order poles? Or is there an infinitude of these nightmarish formula? There is a better way to do it. There are two more ways I will show you. They are very general. The first one is nice. The second one is more computationally useful in a wider array of settings, though not necessarily as clean looking. All right, so proposition 4.1.6. This is a very useful one to know, actually. So if f has an isolated singularity at z0, and k is the smallest integer greater than or equal to 0, such that the limit, I'm going to highlight this in a color like green, the limit as z goes to z0 of z minus c0 to the k f of z exists, then f of z is a pole of order k at z0, we already knew that, and if we set phi of z equals to z minus c0 to the k f of z, then phi can be defined uniquely at z0, obviously it's going to be equal to this limit, it's analytic at z0, definitely, for sure, right? So we can define phi so that it is equal to this limit, right? If we shouldn't really write phi equals this. It equals this everywhere except at z0. At z0 it equals this limit right here, right? Okay. And if we do that, then it's analytic at z0. And the residue of f at z0 is equal to the k minus 1, the k minus 1, phi derived k minus 1 times, evaluated at z0, divided by k minus 1 factorial. Tongue-tied trying to say the k minus 1th derivative of phi. So, okay, we'll get into some examples of this. This is nice if you can, do this well, if you can figure out a nice form for phi, right? Such that you can calculate these derivatives well. If it is, if phi can't be written in a very nice form and calculating these derivatives is difficult, this might not be that useful to you. But if you can do it, it's not too bad, right? Now, the other way, and we'll do some examples. Let's do an example. Here, let's take the residue of z squared over z minus 1 to the third z plus 1 at z0 equals 1, right? So that is a 0 of the denominator here, right? Okay. Poles of order 3, since that's the third, right? Proposition 4.1.6. In this case, phi of z is equal to, well, just everything except for this little chunk in the bottom, right? So that is if you're writing f of z times z minus c0, which is just z minus 1 to the k, right? Such that you can define the limit as z goes to 1, right? Then that k, such that this limit will exist, this k is going to be 3, right? So this is phi. Okay, cool. Basically just take out that chunk. It works for polynomial. Yeah. So let's take a derivative. Take the first derivative, you're going to get out 1 minus 1 over z plus 1 squared. All right, cool. Do another derivative, you get rid of that 1. This will turn into 2 over z plus 1 to the third. And then if you plug in 1 to that, I'll get 1/4. So k is 3. The residue is going to be the k minus 1th derivative evaluated at 1. So that will be 1/4, right? And we'll divide that by k minus 1 factorial. So 3 minus 1 factorial is 2. So this, if you want to see this slightly less confusingly, this is over 2 factorial, right? So 1/4 over 2 factorial is just 1/8. That's the residue at 1. All right, not too bad. Now, if we want to do something a little trickier, if, say, the form of phi here is not conducive to doing a whole lot of derivatives, say it's some super brutal thing and you don't want to just endlessly derive it, or maybe you only know it in a certain way, like a power series or something, and when you do a bunch of derivatives there, you don't really know what that power series is representing or something. You might want to do something like this instead, where you don't have to deal with that. So here, in proposition 4.1.7, we'll have G and H analytic at Z naught with G of Z naught non-zero, and we'll assume that H of Z naught is equal to 0, as are the first K plus 1 or K minus 1 derivatives of H at Z naught. We'll also assume, of course, that the kth derivative at Z naught is non-zero. Okay, so here we're assuming that H has a 0 of order K at Z naught and G has a 0 of order 0, right? Okay, so this is G over H having a pole of order K, obviously, and the residue of G over H at Z naught is given by, and this is a beautiful formula, so cool, K factorial divided by the kth derivative of H at Z naught to the K times the determinant of this crazy matrix. Now, this matrix here will just have the kth derivative of H at Z naught over K factorial, the next derivative of H at Z naught over K plus 1 factorial, K plus 2 factorial, all the way down to H to the 2K minus 1th derivative, or the 2K minus 1th derivative of H at Z naught divided by 2K minus 1 factorial. And then what I'll do is we'll just go over and we will reduce K by 1 as we go, right? And go towards, put zeros in when we get, down past K, right? Below K, we'll put in a 0. Okay, easy enough. Why do we get zeros there? By the way, this is not just like an arbitrary choice. It's because we're assuming that the K minus 1th derivative of H at Z naught is 0. So you really could write the K minus 1th derivative of H at Z naught over K minus 1 factorial right here, and so on all the way down to the 0th derivative H of Z naught over 0 factorial, right here. You just don't have to, because you already know that all these things are zeros in this little triangle above the diagonal, right? And then at the end of it, we will put the G's in the last column, and we will just go down and derive, and of course put the factorials on the bottom, and then we'll take a determinant. Oh, whoa. Nightmarish. I won't make you do this with anything where K ends up being like 50 or something. I won't do that, but you can see why this might be useful, say for like a computer, which wouldn't really have that much of a problem doing this, right? Or at least approximating something like this. Okay, let's do one example so we don't have to feel like it's totally useless. All right, so the residue, let's do e to the z over sine cube z at z equals 0. So obviously K is going to be equal to 3, so we'll use proposition 4.1.7. G of z is e to the z, H of z is equal to sine cube z, and we need to compute H triple prime, the third derivative, the fourth derivative, and the fifth derivative of H at 0. So this is really straightforward because H is sine cubed. It's not too bad. The third derivative is going to be 6, fourth derivative is going to be 0, and the fifth derivative is going to be minus 60. Notice you're going to alternate and have odd derivative 0, right? Because of sines. Well, so whatever, you know how to derive sine, right? And you know how to take powers and all that. So nothing too fancy. Go through and check it yourself if you want. I'm not trying to have us run too late tonight, so I won't write out those derivatives since that's a Calc 1 exercise. So h prime over 3 factorial is 1, or h triple prime over 3 factorial is 1, h quadruple prime over 4 factorial is 0, h quintuple prime over 5 factorial is minus 1/2. And then if we do first derivative of g at 0, or lth derivative of g at 0, divided by L factorial, we'll get 1 over L factorial, right? Since e to the z has derivative e to the z, throw in 0, you'll get out 1, right? So you just get 1 over L factorial there. So if I go through and I make this matrix, we'll get, just looking at everything, we can fill it on in. Since k is 3, we'll get 3 factorial over, and looking up at this, the kth derivative of h at z naught. So this will be, kth derivative here is 3, so that'll be 6, right? Take this, cube it, and then we're taking the determinant, filling everything in. Well, we'll just put it all in there. 1, 0, 1, 0, 1, 1, minus 1 half, 0, 1 half, right? Everyone feeling okay about that? This last part just comes from, you know, the 0th one here, right? So that'll just be e to the 0, which is 1, then first derivative over 1 factorial, we'll get 1 again, then it'll be e to the 0 over 2 factorial, right? So on and so on. And you can fill in the rest of these guys. It's not too bad, and get what you expect. Now we can do a little bit of elementary matrix operations right there, and take the last column, subtract it from the first, something like that, get this into a nicer form. Now when I go through and I expand along this row, when I do this one times determinant of this submatrix, I'll get 0. This one times the determinant of that submatrix, I'll get 0. Then I'll just get 1 times the determinant of this little chunk right here, which is going to be minus 1 times 0 minus the quantity 1 times minus 1. And that obviously just gives me 1 times minus 1 times minus 1, which is just 1. So that's the residue of e to the z over sine cubed z at z equals 0. Kind of cool. All right. You can see why it's useful for computers, or, you know, if someone is very mean to you and wants you to spend a long time calculating derivatives and taking determinants. The final question, though, is what to do with essential singularities. We'll talk about this a little more, but for now, essentially all I have to say to you is that essential singularities are the hard ones. There are no simple formulas like the preceding ones, at least as far as I know. We generally have to rely on our ability to actually find the Laurent expansion to get the first coefficient. We have to at least find the first, that first coefficient, that B1, to do this. Kind of nuts. But anyway, that realistically takes us through the end of 4.1. This is pretty much it. All we did in this entire section is we just, if we zoom out a tiny bit, all we really did is we said, hey, we got this theorem here. That theorem is not so bad. It's a pretty cool theorem. We needed to figure out how to compute residues. We asked ourselves, okay, well, what if it's the simplest possible thing, a removable singularity? We dealt with that case. Then we said, well, what about the next simplest thing, a simple pole? We dealt with that case. Then we said, okay, what about a double pole? Well, we dealt with that in a couple of ways, and we were like, wow, this is messy. Can we get around these messy formulas? And we were just like, yeah, I guess we can do that. We can find things like this right here a little bit better. Or if we need to use computers or something, we found stuff like this, and that is a little bit better for computers, though not as nice for us necessarily, though it is a cool little fact. For essential singularities, things are not quite as nice, and we will need to do more work. So next time we will get further into talking about residues and what they do for us. A little bit more into Laurent series and a few other things, but for now, I think that is a great place to call it quits for the day. I hope you all have a wonderful night. If you have any questions on your homework still, which remember is now due tonight, please shoot me an email. I will answer any questions you have, give you any hints if you need them. Hopefully the couple of problems we did help resolve some lack of clarity if you had any. All right, cool. Have a great night.